Great. Okay. And let me get set up. So guys, if you're able, go ahead and turn your camera on. You can certainly go off camera if you need to, go off for a second, but if you could turn your cameras on when you're able to, so that Forrest has like a more interactive presentation with you all. He's going to be presenting some of his work today, and then you'll have the opportunity to ask questions at the end. So Forrest, I'll do a brief introduction of you, and then we can get started. Forrest Laine is an assistant professor of computer science at Vanderbilt University. And let's see, his research is on the design of numerical methods for the safe and effective deployment of autonomous systems. I'm not sure if that's still accurate, but just check, you can correct me on this information because I think I have an old bio. And then he focuses predominantly on theoretic and algorithmic developments of methods related to dynamic game theory and the application of such methods to robotic systems. Problems Forrest is particularly interested in are those of multi-agent interaction, multi-object tracking, trajectory optimization, and robust machine learning. So you can take it away and correct me on everything I said, because I think that was your bio for last year. So, correct me on anything. But
no, that's great. And that most of that I think is still pretty accurate.
Okay.
So yeah, and that's probably my bad for not sending over a new bio. But anyways, yeah, so thanks to all who are here. I see that my 3 interns are in attendance, which is good. Yeah, so today, there's 3 students that are working in my lab right now this summer. That is Alice, Profil, and Wangju. And they are working on the development, both on the hardware and on the software side of a kind of autonomous quadruped. So that's been pretty fun to see how quickly they've been getting that up and going. But today I'm going to actually talk about something not related to that, which is just more on some of my other research related to some of the dynamic game theory and multi-agent trajectory optimization work that Reagan alluded to in my bio. So I will just share my screen here, something in the chat. Okay, let's see. Alrighty. Now, whoops. I'm sorry. Yeah. Whenever I go full screen, I lose my mouse. That's okay. I don't think I need it for anything. All right, can everybody see this? Okay, cool. Yeah, so today I'll just talk about a paper that actually we're going to present at RSS next week in New York City. So it's kind of recent work. We were mostly working on this over the winter, and this is work that was done with a team of colleagues all over the world, actually. So Lasse was the lead student on this paper, and he is a student at TU Delft in the Netherlands. David is a good friend of mine from when I did my PhD. He's a professor at UT Austin. And Laura Ferranti is an Italian professor. Cyril Staknes is professor in Germany. And Javier Alonso Mora is Lasse's advisor. So this is kind of a weird group that came together. I think that was only really possible because of Zoom and the transition to remote work that we've all come to love, but also hate. So anyways. So yeah, so the title of this work is called Learning Mixed Strategies in Trajectory Games. And this is actually a talk that I'm kind of recycling from a recent presentation that I gave. The content hopefully will be pretty high level, but originally when I made this talk, it was designed for kind of a more senior audience. So we'll try to take it slow. And if you have any questions or you're not really sure what something is that I mentioned or allude to, then just feel free to interrupt and ask what that is. Because I think the purpose of this is to try to expose you to some, ideas in the current research field in these areas, and also just to, teach you a little bit about those areas. So if you're not sure what's happening, then it's not really useful. So just feel free to interject at any time. Okay, so what is the kind of context of this work? So when we set out to start working on this, we were thinking a lot about something that we call model predictive gameplay. And when you think of model predictive gameplay, you can think of controlling self-driving cars, for example. So for example, maybe you're controlling a self-driving car that's driving on an interstate, like you see in this simulation screenshot on the left. So maybe we are this light blue car, which is just a 3D box in the simulation, but we're trying to drive on this three-lane road, and we're in the presence of a bunch of other cars, which may or may not be other self-driving cars. More than likely, these are going to be regular people driving around. So when we talk about model predictive gameplay, this is a generalization of a concept that people usually call model predictive control. And so just a quick recap, so model predictive control is this idea or this technique for controlling a dynamical system, which in this case would be the self-driving car. And the way that that works is that you repeatedly plan a trajectory that kind of plan or predicts forward maybe 5-10 seconds into the future. So this is kind of a short-term, high-fidelity plan. We call this a motion plan. And this plan is optimized subject to some kind of trajectory optimization problem, so that it's kind of optimal in some sense. Maybe it uses not a lot of fuel. It's very smooth and comfortable if you were to go and drive that plan. It satisfies all the constraints, meaning that it's something that's actually drivable by a car. It doesn't crash into anything. It stays in the lanes, etc. So that you can kind of quantify all these different things that you care about when you're driving into these mathematical constraints or objectives, and then you can solve this trajectory. And the idea is that you would solve this maybe a 10-second trajectory into the future, and then you'd only execute the first little bit of that plan, because after maybe the first 1 second of executing that motion plan, you get new information about the world, where all the other cars are, and so you would actually replan. So you're kind of constantly planning 10 seconds into the future, but you're only ever executing the first little bit of those plans. So this is a really effective way for controlling any kind of system that operates in the real world. And this is a technique that's used in all sorts of different disciplines for robotic type stuff like self-driving cars, but also actually this idea really came into prominence in the chemical engineering domains, where people were trying to control these large chemical processes. And things are constantly changing, and anyways. So for driving, this is a really effective technique. But one of the things that I mentioned is that when you're generating these trajectories is you're trying to make sure that they are collision free with all the other cars on the road. And those cars on the road are driven by humans. We don't exactly know what they are doing, what they're trying to do. Are they going to lane change? Are they going to slow down? Are they going to speed up? And in order to kind of write down this constraint that as I plan into the future, right, I'm planning where my car is going to be, over the next 10 seconds. And I want to make sure that nowhere along those 10-second prediction into the future do I ever crash into the other cars. I need to have a prediction for where those other cars are going to be 10 seconds into the future. And so typically what you do is you would, if you were doing this model predictive control technique for generating these trajectories is you would first make predictions for where all the other cars are going to be 10 seconds into the future. And then I would plan my trajectory to avoid wherever those other cars are going to be over this 10-second duration, right? So first I figure out where all the other cars are going to go. And then I plan where I'm going to go so that I avoid them. And this is pretty effective, but what it results in is a very defensive style of driving, which you could argue is a good thing most of the time. And it is mostly a good thing, but there are some times where this fails, right? Because what happens is that when I'm predicting where all the other cars are going to go, they have no idea. I mean, they're doing their own thing, but in the way that I'm predicting their trajectories is totally agnostic to where I intend to drive, right? So this can become problematic on, say, if I'm trying to merge into a congested freeway on an on-ramp, for example, right? So if I say that I'm going to predict where all these other cars are going to go, and they're all going to just drive as if I don't even exist in the way I'm predicting, then they may never make room for me to merge into this congested freeway. Okay. And so ideally what you want to do is you want to say, okay, well, these people driving, they see me, and even though they might be your typical bad Nashville driver, most of the time they do at least acknowledge that you're there, and maybe will slow down a little bit, understanding that you need to merge into the freeway. Oftentimes it seems like people don't do that, but if they're a good play driver, they would do that. And so when we think about how we want to generate these trajectories, right, for the other players, these other drivers, and then for ourselves, really we want these trajectories to be generated kind of concurrently, so that all the trajectories are kind of understanding the existence of each other. And this is where this generalization that we call model predictive gameplay comes in. So what we do is, instead of kind of first generating the trajectories for everybody else, then generating the trajectory for ourselves, we're going to generate all these trajectories at once. So what this ends up being, the way that we do this is we set up a trajectory optimization problem like we had for ourselves, but we set one up for not only ourselves, but for every other car on the road. And this is going to be our kind of model for how humans drive, right? So humans, for the most part, are rational decision makers. Sometimes they're irrational, but mostly you can kind of model them as rational decision makers that are trying to accomplish roughly the same goals as we are, right? They want to drive more or less close to the speed limit. They want to, drive smoothly, not accelerating or decelerating too much. They want to stay in the lane boundaries, et cetera, not collide with other people. So we can set up these optimization problems for everybody, and then we're going to solve this collection of optimization problems all at once. And mathematically, when you have a collection of optimization problems that you're trying to solve together jointly, this forms a mathematical game. Okay. And when we talk about solving games, the kind of notion of a solution is something that we call an equilibrium. And in particular, we usually call these a Nash equilibrium. Okay, so this is a concept that you might have heard before, probably in the context of some kind of economics class or something that you might have taken. But this is a useful concept in this domain too. So the idea now is that we're going to set up this trajectory game. So we're saying, okay, everybody's going to try to optimize their own objective, and they're going to all try to avoid colliding with each other. And then we can optimize and solve for this equilibrium of the game. And the result of that equilibrium is a set of trajectories for all the players in a way that those trajectories are generated kind of understanding the existence of each other. So anyways, this model predictive gameplay is a promising framework for practical modeling of multi-agent interaction. And it kind of gets around this drawback of this model predictive control idea. Okay, so that's model predictive gameplay. Now, as you might have imagined, just by listening to that long-winded explanation, there are some limitations that come up when you try to employ a technique like this, model predictive gameplay. So two big ones that we are aware of, at least, are this notion of scalability and this notion of locality of solution. Okay, so when it comes to scalability, right, what we're talking about is that we have a limited compute budget on the computer of our self-driving car. And, when we think about what it means to solve these problems, we're solving these problems because we want to make decisions. And the faster you can make these decisions and react to the new information that you have, the safer you're going to be. But the more complicated the decision problem is that you're trying to solve, right? And the decision problem in this case is this mathematical game that we're trying to compute an equilibrium for. The harder that is, the longer it takes, and the slower our reaction time is going to be when we're kind of employing this technique. So this is an issue because when you solve these games, it is strictly harder and kind of more computationally heavy to solve these games than it is to solve the more naive trajectory optimization problem. And so that's just kind of one aspect, but two is that there's fewer professional grade solvers out there designed to solve these games. So these mathematical games are just a less common problem formulation than the trajectory optimization counterpart. And what that means is, if you have these optimization problems, there's lots of really good high quality software that you can either download for free or you can license, depending on what your needs are. And these tools are really effective at solving these types of problems really fast. When it comes to these games, you're usually stuck kind of writing your own methods from scratch. And if, even if you are an expert in these types of problems and the numerics behind it, it's kind of challenging to write really high grade, robust solvers without a team of dedicated engineers working on that. So anyways, this makes the time to solve potentially prohibitive, which is kind of a bummer. The other issue is this notion of locality of solutions. And if you've ever taken a machine learning class or any kind of optimization class, and you have heard about the distinction between a convex or a non-convex problem, you might be familiar with this idea of a local optimality, or a kind of a locally optimal solution. Basically, what this means is that you might have found a pretty decent solution that, subject to small perturbations is the best that you could do. But if you kind of think large outside the box, there might be much better things that you could do in a very high broad strokes explanation. That's kind of what this idea refers to. And that's a problem even with the trajectory optimization problems. But when you start getting into the realm of games, this can be a much more problematic issue, because suddenly your solution is making strong assumptions about what other people are going to be doing. Right, so if we look at this little cartoon on the bottom of this slide, you have this van and the station wagon. And you might have two different equally likely or plausible equilibria for the interaction between these two cars. On the left, we could have an equilibrium where the van's going to speed up and the station wagon is going to change lanes behind it. Or alternatively, you could have the station wagon slow down the van slow down and the station wagon will speed up and lane change in front of it. Right. So if the end goal is that the station wagon is lane changing into the lane of the van, either of these two things are more or less equally fine. These are both realistic and plausible. But when we're computing for an equilibrium solution, right, our algorithm is only going to end up choosing one of these. So let's say that our algorithm computes the equilibrium on the left-hand side where the van speeds up and the station wagon slows down. So we say if we're the station wagon, and we're trying to, it's a self-driving station wagon, then the decision that that station wagon might autonomously compute is that, okay, I should slow down and then I should change lanes. But if the van is driven by a human, right, they have their own process for making decisions. And they might think that the best thing to do is to kind of follow the equilibrium behavior on the right. So they might also slow down, thinking that the station wagon should speed up. So basically what you can have is you can have this kind of clash of behaviors, where if the two vehicles were kind of synced up and they were aligned with what they were both going to do, then it would be no problem. But because they're decentralized in their decision making, you can get into these disastrous behavior where, for example, the self-driving car is overly confident about the actions of the other car. So anyways, these are kind of two broad strokes problems that need to really be overcome for these model predictive gameplay techniques to be safe and effective and deployed at scale in these production level systems. So that is basically the kind of context and where this work is coming from. Now, there are a few interesting ideas that have been proposed in the literature in recent years, which have worked to address some of these drawbacks. And one such idea is this idea of mixing over primitive solutions. So what does this mean? If you've ever taken any kind of class that talks about game theory, and you learned what a Nash equilibrium is, you have probably studied this game of rock, paper, scissors. Okay. So rock, paper, scissors is a really classic example of a game in which, similar to what I depicted in those cartoon examples on the previous slide, has no unique equilibrium, right? Because if I play rock, the best thing for you to do is always to play paper. But if you're going to play paper, the best thing that I should do is play scissors. And if I play scissors, then you should actually play rock, right? And you kind of get in this mental loop of what the best thing to do is. And so you can prove pretty easily that there's no kind of stable equilibrium of a action that both players should play in rock, paper, scissors, so that neither can be exploited by their opponent. And so in contrast, what John Nash was so famous for introducing is this notion of a mixed strategy equilibrium, where instead of choosing one action deterministically, you are able to choose a probability distribution over the actions that you play. And if both players are doing this, then suddenly this notion of a unique equilibrium does exist. And it exists in the space of distributions over actions. And so we call this a mixed strategy equilibria. So this problem of kind of being unsure of what to do, should I lane change in front or behind, is more or less the same idea as this rock, paper, scissors problem. And so potentially this idea of having mixed strategy equilibria could be very useful in this domain too, in the driving domain. Now, one of the problems is that unlike rock, paper, scissors, where you really only have 3 possible actions that you could do, when it comes to driving, there's actually infinite different ways that you could drive your trajectory over the next 10 seconds. And so you go from trying to reason about probability distributions over a discrete number of possibilities to a distribution over infinite dimensional possibilities, which becomes, over an infinite set of possibilities, which becomes an infinite dimensional distribution. So mathematically, this is a really weird and ugly thing, especially when you're trying to compute these types of things. So anyways, what some people have proposed in prior work is to basically just heuristically define a finite set of actions that cars can take, right? So just like in rock, paper, scissors, we're just going to constrain a small set of actions that the cars could take, maybe a merge left, go straight, merge right, like you see in this top right cartoon. And then what you could do is you could then basically solve the analog of the rock, paper, scissors game for these two cars when considering their finite set of actions, right? And you'd have some kind of cost function that would score how good the combination of any of these trajectories would be. Just like in rock, paper, scissors, you would have some function that determines who wins given any two pairings of the player's actions. Like in driving, there's no notion of winning or losing, but there's notions of safety or optimality or just good or bad. So you could basically set up the analog of the rock, paper, scissors game for these cars, and you could solve that. And what this paper showed is that this is actually a really effective thing to do. You can get some really nice reasoning about the multi-agent interaction by considering distributions over the actions that you're taking. Now, the problem with what this prior work did is that because they're just heuristically generating these trajectories, right, like left, straight, or right, you actually have to kind of come up with a ton of possibilities, these discrete possibilities, in order to be able to consider all the types of behavior you might want to see. Because, intuitively, going left, right, or straight more or less kind of covers all the things that you want to do. But if you actually watch how cars drive in real life, there's all sorts of nuances in how they drive. And you want to have basically more degrees of freedom than just these three predefined things. So in practice, what they showed is that actually, maybe they consider 200 possible discrete actions so that they basically get a coverage over all the different behaviors that they might want to see. So while in theory, this starts to look like a really nice kind of idea, in practice, the scalability becomes an issue again, because they're actually considering huge numbers of trajectories, most of which are really not what they care about, but they still need to consider that many just so that one of them happens to be the thing that they actually want to do. Or maybe one or two kind of cover the two things that they might choose to want to consider. So the scalability of this is kind of a problem. So one of the, and actually here we can kind of see, this is a little video that I took from a class that I taught last fall, in which I just had students basically implement this exact kind of algorithm, but for a two-player tag game. So we have blue is the player that's trying to run away, red is the tagger. And what you see is that you can kind of observe this nice behavior where the players are kind of able to juke and fake each other out because they're mixing over these multiple possibilities. And so right here, what you can see is that, at this moment, blue is considering weighting between 1, 2, 3 different trajectories, and red is also considering between these 3 trajectories. And what's not shown under the hood is that the way that these trajectories are generated is similar to how described in that example in the previous slide, right? So basically what I did is I just pre-selected these 20 or so goal positions around the edge of the playing field. And the trajectories that the kind of heuristic trajectories that each player considers are just trajectories that are designed to move towards those goals while staying within the playing field. So actually at each instant, each of these 2 players has 20 trajectories that they generate in this kind of heuristic generation approach. And then they play this big, rock, paper, scissors analog, where instead of each player having 3 actions, each player now has 20 actions. So you solve this big 20 by 20, rock, paper, scissors-esque game. And the resulting, what we see is that each player kind of selects to have a distribution over, in this case, these 3 different trajectories. The other 17 trajectories all have 0 weight at this equilibrium. So this is kind of the optimal thing to do. Given these heuristically generated trajectories, blue players should kind of evenly weight, or maybe not exactly evenly, but distribute the likelihood of selecting one of these 3 trajectories according to the weights given here, and same to red. Now, one of the things that you might notice is that presumably both of these players could do better if they had more fine-grained options in this local corner, right? So, as you can see, for example, the blue player and the red player both have two trajectories that are moving up towards these two stars on the top of the playing field. But, presumably if there was a goal in between those two stars, then maybe those players would prefer to choose that trajectory that moves, kind of splits the difference between these two, right? And so, basically what we're observing is that the quality of solution is a little bit limited by the heuristics that we've generated, right? So, and if we wanted to say, okay, well, let's add some more fine-grained trajectories over in this corner, well, maybe we would add fine-grained trajectories everywhere, actually all around. But the ones on the bottom left side of the playing field are not considered at all. They're not useful. So we're basically, wasting computation by generating all these extra fine-grained options that are never going to be used unless we happen to be over in that specific part of the playing field. So this is really the motivation for the work that we did. Excuse me. And the idea was that, okay, well, maybe we could use some, machine learning techniques to basically propose at every kind of configuration that the two players may find themselves in. We could propose candidate trajectories, right? Which in this case, in the previous slide, would be the star, the goal locations. So we could learn some function that generates proposal candidates, so that basically, when we set up this game, we're only considering a 3x3 example instead of a 20x20 or a 400x400 or whatever it might take. And if the way that we propose these candidates is learned well, then actually we can do better than we would if we had this kind of predefined set of primitive trajectories. So the core idea is basically this. So we're going to fix a small number of parameterized candidate trajectories. So let's say 3 per player, right? Because in that previous tag game, we only ever saw that 3 were really needed at any given instant. And then we're going to train what we call a reference generator to predict the parameters that lead to these high quality trajectories. So in this, basically what this means is we're going to, we might parameterize the trajectories by the goal location, as we did in that previous example. And so we are basically going to train some generator to predict those goal locations. Although the idea is a little bit more general than that. We don't have to parameterize the trajectories by the goal locations. We can parameterize them by anything we choose. And then the result is we're going to solve this bimatrix game, which is going to tell us how we should choose our, which of those trajectories that we generated should actually be chosen. Okay. So let me just look at how much time we have, if it's worth going into this. Okay, we're doing all right on time. So when we think about, what I mentioned is that, what we saw is we're using these goal positions as a way to parameterize a trajectory. And in practice, there's more general ways that we could go about doing this. So, let's look at this kind of optimization problem that you see on the top left of this pane. So we have tau star. Okay, so tau is going to be our trajectory, right? Described in some variables. So, tau is basically a kind of, it's some kind of representation that it describes where our system is going to be over time for some finite time duration. And depending on, how we parameterize this, there's different ways, shapes that this can take on, but roughly just understand that this is a trajectory in some abstract sense. So typically the way that you would solve, kind of generate a trajectory is you have some optimization problem, right? Where I'm trying to choose tau that minimizes some objective function, f, subject to satisfying some kind of constraint set, which we define by this set, curly or cursive k. So this is, very kind of abstract way of defining this problem, but roughly this is what's happening under the hood. Is you have an optimization where we're trying to optimize some criteria subject to satisfying constraints. Now, what we show in this paper is that basically you can kind of abstract this away a little bit, and we can come up with some kind of parameter, which we call xi, where you can always choose xi such that if you solve the problem on the right, you will end up with the exact same trajectory as you get on the left. And conversely, if you start out with the problem on the left, you can always come up with xi so that tau hat equals that trajectory. So anyways, this is, I mean, the details are a little bit nuanced of why this is kind of an important thing. But the big advantage that we get from this is that for polytopic constraint sets, which is a kind of very common type of constraint set that you might run into, then given the xi, right, the parameters of this trajectory, then solving for these trajectories is really fast, really quick and easy. Okay, so yeah, I mean, again, the details are not so important, but the big kind of advantage of doing things this way is that you can, you know, try to only offload the learning of our trajectories, only learn the hard part. We're going to basically allow us to kind of online compute the things that we know how to compute really quickly, and we're going to kind of keep that in our problem approach. And we're only going to try to learn the hard things that are not so easy to understand. So again, it's a little bit kind of in the weeds, but it's kind of important part. So okay, let's zoom back out and just think about what the whole pipeline is going to look like, right? So again, the idea is that we have this small set of kind of references, right? If you think back to the tag game, then it's the star locations, the goal locations. We have a small number of these that some kind of learned generator is going to propose. So if we have two players, x1 and x2, representing the kind of positions of the two players in a game, then we have two reference generators, right? So this is the pi theta 1, pi theta 2. And these are functions that are predicting where we think good goal positions are going to be, not only for player 1, which is kind of we can think of as ourselves, but also we're going to predict what we think are the good goal locations for player 2, which is our opponent in this case. So given those kind of candidate goal positions, we can generate the candidate trajectories for both players. And that's what comes out of these traj1, traj2 blocks. Okay. So the result of this is that we have maybe 3 candidate trajectories for each player: tau 1, 1, tau 1, 2, tau 1, 3, and tau 2, 1, tau 2, 2, and tau 2, 3. From these kind of candidate trajectories, we form the resulting kind of cost matrices that result in this you know, rock paper scissors-esque game. And we ultimately solve that rock paper scissors-esque game to come up with the appropriate weighting selection on how, you know, what are the probabilities that we should use to select our candidate actions. Now, one of the things, or the kind of key insight to this whole pipeline is that we can actually differentiate through every single step in this pipeline. And what that means is that we can go from the resulting cost that we see from solving this thing at the end. These are the L losses that we get at the end. And we can backprop that signal all the way to our generators, the pi theta 1 and pi theta 2, so that we are kind of always improving how we propose those candidate goals. So what this means is that when we start learning, right, we go out there and we say, okay, we're going to generate some candidate actions. And at first they might not be very good, right? We might propose bad goals for ourselves, and we're going to propose bad goals for what we think our opponent wants to do. But then every time that we run this pipeline, we can actually back propagate and we can update the parameters of that generator to basically improve our predictions of what we think are good goal locations for these things. And ultimately, this works super well. You can get a very strong learning signal very quickly. So I think, okay, there's some videos at the end, I guess. So we'll get there, but I guess quickly, we can just kind of recap. So we evaluated this idea on this very same tag game that we showed that video from the class assignment. But we just made it a little bit more interesting. So there's some kind of different environments that the players can operate in. And we have some 3D versions or multiplayer versions of this. But anyways, the basic way that this game is defined is that there's an objective D, which is basically the distance between the two players. And this is a kind of min distance over time. And we have the pursuer is trying to minimize that distance, and the evader is trying to maximize this distance. So this is something that we call like a generalized zero-sum game. And what we found is that our proposed approach does kind of do what we expected it to do, what we wanted it to do. So namely, what we found is that using these kind of 3 fixed options or even 2 fixed options, if we were able to learn how to update those options based on the configurations that we were in, this was able to beat out very large numbers of candidate trajectories that you might have, right? So remember that the one option that we could do is we could just have hundreds of goal options surrounding our playing field so that we're always considering a ton of options. But we found that even no matter how big we made the number of baseline trajectories, just having 2 or 3 that we could adapt to wherever we were was always going to be better than that. So that was something that was pretty interesting. Another thing that we found was that this notion of being able to consider multiple trajectories was much more performant than the kind of other baseline, which was just simply not having multiple options considered at any time, but just choosing a single option. So the ability to generate multiple candidates and then kind of play this rock, paper, scissors style game always outperformed the baseline, which was just to generate a single trajectory and try to make that trajectory do better and better, which would be kind of the standard reinforcement learning style. So the third kind of big takeaway is that, like I said, the learning signal that we get from this is very strong, meaning learning is very quick. So we can actually learn online. And here, I think there's a video here. So this is learning completely from scratch. So the 2 players at first kind of, don't play very competitively. But even after here, we're at only about 50 gradient steps, and the players have already kind of figured out how to play decently well. And I think this is going to speed up here in a sec. I forget which video this is, but I think, oh yeah, here we go. So basically we play, so I think we play for about 1,000 times steps, which in the scheme of regular, reinforcement learning style approaches is really minuscule. Most kind of existing reinforcement learning techniques, require millions or more learning samples. So actually, I'm just going to kind of replay the last little bit here. So after about 2,000 steps of training, the players learn like very effective techniques for evasion and pursuing, right? So they're kind of doing this juking behavior that we saw before with the fixed number of trajectories, but they're going much faster and kind of playing at a higher speed and competitiveness than before. Here we basically show that again, this lifted version where you're able to consider multiple actions, so you're able to adapt, outperforms other baselines, right? When you're playing against a player who is, has their own methods for generating actions. And then finally, the last thing I'll mention is that we, since basically working on this paper, we've been working on some extensions to handle many players, right? So not only 2-player games, but games with lots of players. And there's some really interesting kind of ways that changes the math and some of the methods that we computed. But beyond just the math being cool, it also results in these really nice games where you can reason about interactions of lots of different players in a really efficient way. So again, this is learning, this is the behavior of all of these agents, which are trying to kind of go to their own goals while avoiding colliding with anybody else. This behavior was generated after only, again, I think 1,000 training steps. So you can get some really nice interactive behavior that pops out very quickly from this type of learning. And again, all of this whole pipeline is super efficient and designed to be solvable in real time on kind of standard hardware, which is was a big thing that we cared about. So, and that's true both for the forward play, like at convergence, but also during training. It's also efficient. So anyways, just to recap, as I kind of come to a close here, what I talked about was a method to efficiently learn mixed strategies for trajectory games. And so this is the idea to be able to kind of effectively learn how to propose a few candidate actions in these infinite dimensional spaces so that we can still play these rock, paper, scissors style games, but do so in a way that's computationally efficient. We focused our method on learning the hard parts, which really boils down to the interaction part, and then allow our computers in real time to compute the easy parts that we know how to do really well, which are just the kind of single player trajectory optimization problems. Formulation addresses the 2 key challenges that we are aware of the existing techniques, which is the scalability and this idea of only considering single evolutions of the future. So that brings us to the end here. And I think we still have a few minutes, so happy to take any questions or chat about any of this stuff. Thanks for listening.
Yeah, thank you so much, Forrest. Great presentation. And again, opening the floor to questions.
Could you explain what the game value is and how you calculate it?
Yes. Are you talking about here
Oh,
or in this slide?
here, these slides.
Yeah, okay. So game value in this case was simply the this is so if we go to here, so the game value is the expected value of D of tau 1, tau 2. Right, so D is considered pairwise between trajectories. So for in this example, both players have 2 trajectories. Then there's a distribution over the different combinations of these 4 trajectories. And what the game value is basically the expected value of that function D of tau 1, tau 2. And the reason that we call it the game value, because you might think that that's the kind of value for one single player, but because this is a zero-sum game, this is the negative of this value could be considered the value for the other player. So the single number kind of quantifies how both players are doing. So what you see here, excuse me, is that the game value is higher for our version than the baseline, which basically in this case corresponds to the evader playing better than before. And that's kind of what we would expect here, because this game is set up where if you are only able to consider a single action, then and you are the pursuer, the person trying to tag, it's much easier to exploit what the opponent is doing if they're not able to kind of do these juking behaviors or juking maneuvers where they're kind of, have multiple things that they're going to kind of randomly choose between. So if they're not being unpredictable, which is really what this method allows agents to algorithmically embody, then the pursuer has a huge advantage. But we see that when the agents do have this ability to kind of act unpredictably, then it creates a big advantage for the evader. And this is something that it's a little bit hard to talk about how to measure competitiveness of a game. Because, for example, you could have two players who, are both really bad at the game, and the resulting, value for each of those players could be the same as if both players were really good, but they were equally balanced. And so we found that this was something that was an interesting metric that kind of showed the advantage that our method endowed the players, which in particular the evader in this case. But for some other games that we've explored, there's different types of advantage that they come out of this formulation.
That's cool. Thank you.
Yeah, you're welcome.
Other questions?
I have one more.
Yeah.
Could you explain the definition of a game again?
Yes. So the way that I like to think about games is, different people will tell you different definitions. But mathematically, when we talk about these games, the way that I like to think about it is any collection of optimization problems that need to be solved together. And you can come up with different ways of organizing these optimization problems. But basically, anytime you have more than one optimization problem that are kind of independent but related in some way, this constitutes a mathematical game. And so obviously, in order for this definition to hold, you need to have a definition for an optimization problem. And an optimization problem, for example, is what you would see here on this top left. So here we were talking about it in the context of a trajectory, but really in this formulation, tau could be anything, right? Any kind of decision variable, any variable that constitutes the decision that you're trying to make, right? So an optimization problem is something where you have an objective, right? So you're trying to minimize some objective function, and you have constraints that you need to satisfy. So that, in its most general form, is an optimization problem. And if you have multiple of these optimization problems, basically representing decisions that need to be, independent decisions that need to be made by independent entities, then that is what defines the mathematical game. Right, so a game is really trying to model how multiple decisions are made by multiple players at the same time. And there's all sorts of really interesting ways that you can define games. You can have different ways of organizing the decisions by players, right? So you can have leader-follower games, which are known as Stackelberg games, where you have one player kind of gets to play first, and then the other player plays second. And so trying to think about what the player one, the leader, should do, understanding that player two is going to then act rationally in response. There's some really interesting ways to analyze that. You can have these Nash equilibrium games where everybody plays effectively at the same time. So that leads to a different type of analysis. And then you can have all sorts of different weird ways of structuring these things. You can have repeated games where players are kind of repeatedly making these optimization problems and so forth.
Thank you.
I had a question. Right.
Oh. So Aryaman, we can kind of just barely hear you. So I don't know if you have a better
I'm audible now?
Yeah, that's better now.
Yeah.
Right, okay. So my question was about the practical implementation of this. So did you use DDQNs or DQN networks for your entire model, or was it something else?
No, so no, we had no Q networks or anything like that. the only neural networks that we had in this whole pipeline were basically these pi theta function approximators. So these, in practice, these pi thetas were both relatively small neural networks, and all they did were they were just some kind of neural network that went from state combos, so x1, x2, which in this case were relatively low dimensional signals, right? They were the the state values for both players, where in these kind of tag games, the player is represented by a 4-dimensional state vector if it's in 2D, or it would be 6 dimensions if it was in 3D. So together you have either 8 or 12-dimensional input to these neural networks, and then the output are these relatively high dimensional parameterizations of a trajectory, and you have multiple copies of them. So all these pi thetas really are just these, well, I mean, in this exact example, they were just simply fully connected neural nets with a few layers. And I forget what activations we chose, played around with a few different ones, but they didn't have to be too complicated at all. But the loss function that we get was kind of directly computed from this L1, L2. And it all kind of stemmed directly from the rest of the pipeline, which is relatively traditional in the way that we set everything up.
Thank you.
Yeah.
All right, real quick, Forrest. So are you teaching any courses at Vanderbilt this coming school year, this coming spring or fall?
Yes. So in the fall, I am teaching a course that's it's called Extended Mathematical Programming. So this is a course that I taught. It's going to be kind of like version 2 of a course that I taught last fall, which last fall it was called Computational Game Theory. But this year I changed the name because we're going to kind of broaden the scope a little bit. And so, like I said before, a game, we like to think of it as a collection of optimization problems. And mathematical programming is the discipline of studying algorithms for solving optimization problems. And extended mathematical programming is the discipline of studying algorithms for solving collections of optimization problems. And so you could call it computational game theory, but a lot of the problems that we find, while you could think of them as games, are a little bit more general. And so we call these extended mathematical programs. But anyways, that class should be pretty fun. So we're going to talk about Nash equilibrium problems, Stackelberg equilibrium problems, mixed integer programming, multi-leader, multi-follower games, stuff like this. So that'll be taught in the fall. I think that's like a graduate level class, but I think it's still open to undergrads if you want to take that. But I just recommend that you have had some experience with optimization before. And then in the spring, I'll be teaching again a class on self-driving cars that I taught this spring. And that class should be pretty fun. We're actually trying right now to acquire a real self-driving car that some friends of mine have graciously offered to donate. So if everything goes to plan, then there'll be some labs and final project in that class in the spring where you will get to write algorithms and deploy them on a real self-driving car that will drive around in the parking lots of Vanderbilt. So you should sign up for that class if you're an undergrad, for sure.
Yeah, thanks for sharing. That one sounds like a definite, fun one to be in. So, all right.
I hope so.
All right. Well, Forrest, thank you for sharing with us today. I think that's all we have time for. We really appreciate you taking the time out of your summer schedule to be with us here. And a couple of quick announcements for the interns. So a few things happening this week. Number one, if you are planning on going to movies in the park in Elmington Park tomorrow, if you're driving there on your own, we're going to meet up as a group at 7. If you need a ride, let me know and I will collect addresses from you, and probably start picking up those who need a ride, like starting at 6-ish, depending on how many people need picking up. Be sure to bring money because there's food trucks and games, etc. And then, on the big screen, it'll be playing Encanto if you haven't seen that. As well, Diego Manzanas Lopez, his PhD dissertation defense is tomorrow at 9:30. So we're going to, you guys have the option to attend that in lieu of the lunch and learn that we would normally do. And also timesheets are due on Friday. So if you have any questions, feel free to ask me now or later in Slack or via email. All right. Thanks, everybody. Thank you again, Forrest.
Thank you. Bye-bye.